Hello, everyone. My name is Gorchalyan, and we are hosting online webinars, quantum photonics and its applications. So today we will talk about quantum fluids of light and about polaritons. So our first speaker is Iacopo Carusotto, who completed his PhD in 2000 at Scuola Normale Superiore in Pisa, Italy, and then carried out postdoctoral work at Kastler Brossel Laboratory of École Normale Supérieure in Paris. Since 2003, he has been a researcher at the INO-CNR BEC Center in Trento, Italy. He has been an associated researcher for CNRS in France and a technology and a visiting professor at the Swiss Federal Institute of Technology in Zurich. His primary scientific interests include quantum fluids of light, topological photonics and physics, and the study of analogs of gravitational phenomena in atomic and optical systems. Please, Professor Iacopo, the stage is yours.
Okay, thanks a lot, Go, for the introduction, and thanks a lot to Tatev for the invitation. It's for me a great pleasure to be with you today and discuss some exciting physics, and I hope this is a beginning of some more in-person activity that we hope to be able to develop all together in the coming years when all the sanitary situation in the world would go back to a sort of normality. So today, the plan of the lecture is to introduce you to this concept of quantum fluid of light. So normally, the idea of fluid make you think to a material fluid like water or air, or if you wish, liquid helium. So something which is formed by material particles. So if I do a sketch, I have a box with some material particles inside. And our fluid is formed by a large number of particles which interact with each other. Say we have a large number of particles. They have a mass and they interact. So typically, when you study kinetic theory of gases, you have these particles which move around in your box with random velocity, and from time to time they collide and scatter at some angle, and this scattering is what is responsible to obtain a collective behavior in this fluid. In water, the situation is even more interacting because the particles are really close to each other and they don't have much time to travel between two collisions. So in any case, our intuitive idea of a fluid is based on these ingredients, many particles which have a mass and they have typically binary interactions. So do you think that light can be described by this picture? So normally light is formed in a quantum picture by what? Basically, it's a lot of photons that I draw here that basically propagate in vacuum with a speed which is basically a speed c. So let me say here photons. So light is formed by many photons, so many photons. So the idea of having many particles is present, but what about the two other ingredients, being massive and interacting? So concerning the mass, that's a bit of a tricky issue because light is formed by massless particles. So normally you learn from classical electrodynamics that light propagates at a speed c. So a speed which is always c, which is typical of massless particles. at the same time, photons in vacuum are described at the usual level of approximation by Maxwell equation. And Maxwell equations are known to be linear. Linearity of the equations means that if you take two solutions of Maxwell equations and you sum them, the result will be again a solution of Maxwell equations. So if I have a laser field which travels in this direction and another laser field which travels in this direction, and I make them cross, the result would be just two laser fields which keep propagating in the initial direction. On the other hand, if I do the same experiment with particles, I send a beam of atoms vertically against a beam of particles horizontally. They hit each other, they will scatter and will bounce on each other and give all the products of scattering that we are used to consider in any physical problem, or that we have when we throw two soccer balls against each other. They will basically bounce against each other. So these conditions, this massless nature and the linearity of Maxwell equations seem to be conditions which are incompatible with the idea of fluid. So at this point, this seems to be the end of my talk. So from this, one would say it's impossible to have light behaving as a fluid. So there is no hope of realizing anything like a quantum fluid of light. But actually, there are some hidden assumptions on what I wrote here. Let's start from the mass. So normally, of course, we know that in free space, say, photons travel at speed c. But what in waveguides? So people who have some expertise in, say, photonics know from experience that waveguides are able to confine the propagation of light in a given direction, in a given region of space, and actually strongly modify the so-called dispersion relation of light or of photons. So to make things simple, let us consider the simplest configuration, basically two mirrors. You have two metallic mirrors. And you have an electromagnetic field in between the two mirrors. And suppose the mirrors are very close to each other at a distance which is comparable to the wavelength of light. So in order to satisfy the boundary conditions on the electric field, which has to be zero at the metal, you have to choose for the photon a profile for electric field which has nodes on the metallic mirrors. So in the vertical direction, the field, say along z, I call this z, this will have a form something like a sinus of something kz times z. So imposing the boundary conditions here forces the field to have a wave vector which is non-zero along the z direction. Or in other terms, if you want to have light being between the two metallic surfaces, you have to build a solution which is the sum of two waves which go back and forth in the vertical direction. So this is something that you are obliged to do to satisfy the boundary conditions at the metallic mirrors. Mathematically can be re-expressed in terms of the so-called dispersion of light, of photons, as a function of the wave vector along the parallel direction. along the mirror direction. So if I trace the frequency of a photon as a function of the wave vector along the horizontal direction, as a function of the in this direction, we get something which has the form of this kind of dispersion. It tends to omega equal ck at large k, but at small k, it has a finite curvature. Okay? So if you work out the mathematics for the propagation of waves between two metallic mirrors, you can write the dispersion as omega square equal c square times kz square, which is fixed by, in this formula, by the distance between the two mirrors. So I can write it in other words as pi square over L square, where L is this distance, plus kx square plus ky square. So if you work out the mathematics of light propagation in between the two mirrors, you get something of this form. Okay? So let me add an h bar. Omega, h bar omega is equal to c square times h pi over L square plus px square plus py square. And here I call it h bar omega, I call it e square, where e is h bar omega and p is h bar k. So you recognize the energy and the momentum of a photon. And you see that this law, this relation between the energy and the momentum is just what you learn from relativity, where you interpret this term as mc square. It's a mass term. So the dispersion of a photon in between two metallic mirrors is analogous to the dispersion of a relativistic particle with a finite mass. So physically, this means that whenever you confine light between two mirrors, the photon acquires an effective mass due to the confinement. So at the end, the motion of the photon along the cavity plane can be described as a relativistic particle with a finite mass. As a parenthesis, I can mention that the similar arguments are used in high energy physics, where there are some people who pointed out that one of the possibilities of the origin of mass of particles could be from confinement of these particles field in some extra dimension between the 3+1 physical dimensions that we see every day. So if you think of particles living in a higher space and being confined along the extra dimensions, this could give rise to an effective mass of particles. Good. So this should have convinced you that photons in cavity have a mass which is different from zero. So the problem of the effective mass of photons is solved. So we have obtained a way to just give some mass to a photon by confining them between two mirrors. So the first problem is solved. So we are left with the other problem about interactions. So let me go back to the question about the Maxwell equations. I told you that the Maxwell equations are linear. So the sum of two solutions of Maxwell equation is again a solution of Maxwell equation. So I have e to the I k1 times r and e to the I k2 times r, which basically is one photon going in this direction, one photon going in this other direction. If I sum the two, I have a solution with these two waves which cross each other without interacting. So Maxwell's equations predict no interactions between beams of light. So how come that photons can acquire an interaction? So this reasoning is at the level of Maxwell, so at the level of classical electrodynamics. But if you go beyond that and you study quantum electrodynamics, QED, for which I strongly suggest Feynman's book, which is titled QED. It's a great introduction to quantum mechanics and quantum electrodynamics in particular. You see that there are some diagrams, some Feynman diagram of this form. A photon, two electron positron. So this diagram. You see you have one incoming photon, another incoming photon. They exchange a pair of electron positron. If you prefer, I can draw it again in perhaps a more explanatory language, which is this. So you see the first photon arrives, it's annihilated and creates an electron-positron pair. This electron scatters on the other incident photon. Then this positron scatters emitting a photon, and then recombines at the end with the other photon emitting another photon. So if you look at this diagram from outside, this diagram can be seen as an interaction between two photons. So QED predicts that photons are interacting particles. This is kind of very unexpected and very little known, but it's a very classical result, which was first predicted by Heisenberg, so Werner Heisenberg, and his student Euler, which is not the Euler. It's another Euler which had much less luck in his life as he died in World War II. But before going to war, he did his doctoral work with Heisenberg, and they predicted the possibility of photon-photon scattering with a cross-section that I'm writing here, sigma, which goes as alpha to the fourth, which means that we have 4 vertices of light-matter interaction. Then we have some length, which is the Compton wavelength. And then we have h bar omega over mc squared to the 6th power. Good. So you see here that for photon frequencies, which are much smaller than the electronic mass, this process is extremely suppressed by a 6th power. For instance, let's make a specific example of visible light. So for visible light, this object is 1 electron volt. This is the mass of an electron, which is, say, on the order of 1 mega electron volt. So you see that this factor is 10 to the minus 36, which basically means 0. This process is completely unobservable with visible photons. And that's why in Maxwell's equations, we see that photons are actually non-interacting particles, and Maxwell's equations are indeed linear. What are the way out from this statement? But one can do basically two things. One, you see here is sigma is alpha to the fourth, which is blocked. Then you have some Compton wavelength square, which is also blocked. And then we have h bar omega over mc square to the sixth. So one can, in order to improve the situation, one can either act on this numerator. So if I, for instance, I go to the gamma rays, in the gamma rays, this h bar omega can be large. So one can actually improve the signal just by pushing the experiment to higher energies. So, but this is difficult because one does not have easy access to lasers which operate in the gamma rays region. The other possibility is to work on this denominator. So why this denominator is there? If you look here, this diagram, these intermediate steps in the perturbation theory underlying the Feynman diagrams are all detuned by something of the order of mc square. Because you see, for instance, here, you have a photon which is annihilated and creates a pair of electron positrons. So one has to lend to the system some extra energy of the order of mc square, because energy is not at all conserved in this first process. Of course, in quantum mechanics, you can borrow some energy if at the end you give it back. And this lending of energy is only possible for short times by the energy time uncertainty rule. So, but anyway, these intermediate steps have a very high detuning, so they give rise to this large denominator. So if in the intermediate steps we have, say here, I draw again this diagram. If in the intermediate steps I have electron-positron pair, these would be very difficult to achieve because electron-positron have an mc square which is of the order of 1 mega electron volt. So what could be the way out to reduce the value of this denominator? Any idea? So you know from solid state physics that electronic states in a solid can be classified in a conduction and valence band. This is, say, the frequency, and this is, the, say, the wave vector in a solid. And a typical semiconductor is something where all the states are filled in the valence band, and the conduction band is completely empty. Okay? So what are the lowest energy excitation of this solid state material? So you see here, you can promote an electron from here to there, which in other terms correspond to create an electron and create a hole. So instead of creating, like here, an electron-positron pair, you create an electron hole pair in a solid. And how much is the energy of an electron hole pair in a solid? It will be of the order of the energy gap of the solid, which for standard solids is of the order of electron volts. For instance, if you work with, say gallium arsenide, and you work with light, which has a frequency of 1 electron volt, and you create an electron hole pair whose energy is of the order of 1.5 electron volt, you see that for this choice of parameters, this guy is no longer 10 to the minus 36, but it's replaced by 1 over 1.5 to the 6th, which is of order of 0.2 or something like that. So it's a number which is extremely large as compared to 10 to the minus 36. So you see that these processes were the same processes where in between you create and the electron hole pair become actually experimentally observable. So this means that in a semiconductor medium, photons actually interact with each other. So they become interacting particles, similarly to what happens to, for instance, molecules in air. So if you take a chunk of semiconductor medium, you shine 2 laser beams from 2 different sides, they will collide and they will scatter in any direction. So what is the name of this process in optics, in nonlinear quantum optics? You see, this is a process where 2 waves enter and 2 waves exit. So the name will be 4-wave mixing. It's a kind of trivial name, which is well known in optics. It's called the 4-wave mixing. So 4-wave mixing in the nonlinear optics language is the same as photon interaction in a particle picture. So we are basically done. We have found a way to obtain a sizable photon-photon interaction just by letting light propagate in a medium. If we combine this with a cavity, for instance, taking 2 mirrors and filling the space in between by some material, so this is a nonlinear material. These are mirrors. This is basically a platform. Here, photons are massive and interacting. Great, we are basically done. We have all the ingredients to have a fluid of light. We have all the properties that are needed for light to behave like a fluid. So there's been a lot of research on this stuff in the last years. So what I'm going to tell you now are just 2 experiments, which in my opinion are most interesting and give a good idea of what can be done with this stuff, and give an idea of the perspectives of this field. So the first experiment is for superfluid light. super fluid light. So superfluid means a fluid which is able to flow without friction. And the most known example is helium-4, where you can make a flow of liquid helium around an obstacle. So if you put an obstacle in liquid helium, helium will be able to flow around it with no friction. This, of course, provided the velocity is smaller than some limiting velocity, which typically takes the name of Landau velocity, taken from the name of Lev Landau. So what happens in light? Exactly the same. So what people did was to take a cavity. Basically, they create a fluid of light in this cavity by shining some laser beam at some angle. In this way, one can create some fluid of light here, which moves in some direction. If one adds a defect at some position in the cavity, here, depending on the speed, if it's smaller than the speed, the Landau speed, light will be able to go around the defect without friction. If the flow is too fast, there will be friction. So to this purpose, I want to show you here some images. So let me go to Can you see my image?
Yeah.
So you see here that in this region here, there is a defect. It's basically here. So these three pictures are for different densities in a fluid of light. In this right picture, the density is so large that the speed of flow is smaller than the Landau critical speed. So basically, the light can go around the obstacle without feeling any special friction. Here instead, the light particles come to here, hit the defect, and are scattered in all directions. This scattering is responsible for these fringes. And here, for an even larger speed, these fringes are more and more visible. So this one goes from a superfluid light regime to a regime of non-superfluid, just by increasing the speed of light, as compared, of course, to the speed, the Landau speed in the fluid.
Before you continue, can I ask you a question?
Of course, sir.
So the question is about colliding of two photons. So can we somehow light two photons in the medium so they don't feel that they are in the medium and they don't collide? Are there any ways?
Oh, of course, you can choose media where these interactions are weak. So there are a lot of media where this effect does not happen because of different reasons, because the electronic gap is very big, or because you use polarization degrees of freedom in a way not for them to collide. So actually, this is a sort of normality that they do not collide. In order to make them collide in an appreciable way, you have to make some efforts. So I made a kind of simple history from the reality, which is a bit more complicated.
Okay.
But there are even materials where you can, for instance, use some electric gate to tune the amount of dopants which are present in the material, and in this way to tune the interaction from low to strong.
Okay. Thank you.
Good. So what I showed you was indeed that if one has a defect at some point, if the speed of light is smaller than the critical speed, light basically go around without interacting, while if speed is large, there is a lot of scattering, and this scattering gives rise to those fringes that we have seen before. While here, basically, there are no fringes. And this absence of fringes is the consequence of superfluity. So actually, the superfluidity is a collective behavior which is due to the interaction between the photons. And in this way, the collective behavior is able to screen out the presence of the defect and make the photons flow around the defect with no scattering. While here, there are fringes, and these fringes are basically the signature of friction. And this critical speed, this is determined by interactions. The lower the interactions, the smaller the critical speed. So it's a collective effect which is determined by interaction mostly. Okay? Good. So this is a regime where light behaves as a collective gas of many particles interacting with each other. Now, the next challenge, which is presently the big challenge in the community, is to obtain a sort of hard sphere behavior for photons. So what do I mean by hard sphere? Basically, I mean photons which behave as billiard balls, really like hard objects which are impenetrable. Is it possible to obtain this? Which is absolutely the opposite regime from what one learns from Maxwell. Impenetrable means that there cannot be two photons at the same position. In order to do this, people are using a very simple trick, which is the so-called photon blockade effect. The photon blockade effect is easiest understood in an optical cavity. Let me consider a single mode optical cavity with some nonlinear material inside. And let us consider that the cavity frequency omega is some bare frequency plus some nonlinear frequency multiplied by the number of photons which is present in the cavity. And you see that if you have interactions between photons, it's basically amount of having some interaction energy between them. So a shift in the photon frequency. Okay? So if I draw the level diagram of this cavity, I have the state with 0 photons, the state with 1 photons. The state with 2 photons is not add twice the energy of 1 photon, but it's shifted by the nonlinearity, by omega. It's shifted by omega non-linear. So what happens if I shine a laser which has this frequency? So the first photon can enter the cavity. but the second photon cannot, because this mode is out of resonance. So actually, this cavity can only contain at maximum one photon. So no two-photon excitation. So basically, this means that photons behave as impenetrable photons, impenetrable particles. So experimentally, how can you detect this phenomenon? But typically, people shine a laser beam on here, on the cavity, and then look at the light which goes through the other side. And one makes a detection of the two photon correlations at a distance of time t. So this object is basically the probability of detecting a photon at time t and another photon at times t plus small t, probability of detecting. So if you find that this object, this is a proportional to, is a proportionality link. So if you find that the photons arrive very spaced in time, this is the time axis, so never two photons together, always well separated. This formally is encoded in G2 being smaller than 1 and is called anti-bunching. So photons do not like to arrive in bunches of many photons. And this anti-bunching is a signature of the fact that two photons cannot be in the cavity together. Because you see that if one photon is in the cavity at each time, when you detect one photon going through, you have to wait for the cavity to reload before being able to detect the second photon. So really, photons behave as particles which cannot sit together at the same spatial location. And this is called photon blockade. A single photon blocks the entrance of another photon. Good.
Can I ask a question, meanwhile?
Of course, Tatev, go ahead.
Yeah, maybe it's a very naive one, but what is the time between the photons to be reloaded? Does it depend on the material or the cavity length?
It depends on, exactly as you're saying, it depends on the cavity length, but mostly on the reflectivity of these mirrors. Because in order for the cavity to reload, you need the photon to enter from the incident beam into the cavity.
Yeah.
And typically this time tau to reload is of the order of Q factor divided by the frequency of the cavity. So the better the Q factor, the longer it takes to reload. Mm-hmm. And then this time to the separation between arrival photons.
Yeah, but in that case, for instance, while exciting, when you literally pump the photons inside the cavity, you do not pump one photon at a time, but you pump a bench, right?
You're pumping with a classical beam. But if you think of this pumping as injection of photons which are coming from this classical beam, you see that the first photon will enter the cavity and will be there. But the next photon cannot enter, so it's forced to go back. So once this photon inside has gone through, then another photon can enter.
Okay. All right, I get it.
So this photon blockade is the way to make photons to behave as strongly impenetrable particles. So impenetrable objects. which is a completely new regime for photons, very different from what one expects from Maxwell's equation. So there is at the moment, there is a big effort into exploiting this photon blockade, to have a photon blockade, to obtain the so-called strongly interacting fluid of light. You know that when you have a fluid of many particles which interact strongly and are cooled to very low temperatures, there are a lot of phenomena that can take place, and where the quantum nature of the photons start being really important. So one can obtain states of matter which resemble the very peculiar states of electronic matter that one finds in low temperature physics. For instance, the most exciting one at this moment are fractional quantum Hall fluids, that in electronic physics originate when a gas of strongly interacting electrons is cooled to millikelvin temperatures in the presence of an external magnetic field. Here one can try to do the same with light, provided one has the way to obtain low temperature light, which is kind of possible by using very quiet laser sources, and exploiting photon blockades to get the strong interactions. So this is really one of the holy grails of quantum optics these days. So if you are excited by this physics, just stay tuned that we expect some very important breakthrough to come out in the coming years. Good. So with this, I think I've given you a kind of a broad idea of the field. If you want to know more, you can look at the review paper that I wrote with Cristiano Ciuti. It's on a review of modern physics. It was written in 2013. It's not really the most updated one, but it contains all the basic concepts. It's also available on the archive in 2012. And it contains all the concepts that I presented you today in the whole talk. So it's a very good place where to have a look and learn more. Then if you have more specific questions, don't hesitate in dropping me an email at my email, which is my first name, family name, at universityoftrento.it. Good. And I thank you for your attention, and I'm happy to answer any questions you may have. Thanks.
Okay, thank you for your talk. I think I have another question. So can you go back to the slide of blocking second photon by the first one? So the photon blockade, yes. So is it possible for the second photon not to enter the cavity and be as well detected as the first one at the same time?
Of course, if you put another photodetector here.
No, not there.
Then you mean here?
Mm-hmm.
So the photon which cannot enter the cavity is forced to reflect.
The question is it possible for photon not to reflect? Somehow avoid the situation of reflecting.
You know, the photo, you could do another scheme where the presence of the first photon makes the second photon being absorbed. That's also something which could happen.
Mm-hmm.
But the very presence of photon blockade means that the first photon changes the properties of the cavity in a dramatic enough way for the second photon to behave differently from the first.
Okay.
That's the very definition of photon blockade. Of course, if you have a standard cavity with no material inside, then the photons will basically enter one, then it goes up, out, and the second one enters, blah, 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 completely independent from each other.
Yeah.
That's what Max's equations would predict.
Okay. Thank you for the answer. So are there any other questions? Oh, I see Tate there rising.
I do. Yes.
Please, Tate.
I have a question about the quantum Hall fluid. So when we talk about photon fluid, so we kind of assume that they are particles. But the Hall, doesn't it mean that there is nothing, the empty space? So when we talk about fluid of Hall, how do we understand that to, I mean?
You mean here the quantum Hall fluid?
Yeah.
Oh, no, so this is the name of a person. It's called Mr. Hall, which basically predicted.
Okay.
So this is, if you know, when you have a piece of material, so you put a voltage. Say, you put a voltage between here and here. So you get a current which goes in this direction. And you see the whole voltage is basically that. See, not here. You see that it emerges a potential difference between these 2 points. So this is the V longitudinal, this is V transverse. So the whole effect means that if you have a current I, you will have a voltage V transverse, which is proportional to the current I times a transverse resistivity. This is the whole effect. And this basically happens because electrons in a magnetic field feel a Lorentz force.
Yeah.
So you see electrons are pushed in this direction, they feel a magnetic field, so they are deflected on one side. This is the whole effect. And the quantum Hall effect basically is a quantum mechanical version of this, where this object is a rational number. So it's not a generic number, but it's a rational. So it's a fraction of small integers.
Oh, okay. And now the research goes towards the magnetic field. So the effect of magnetic field on the,
on the photons. And you know, the photons are neutral objects. So having a magnetic field is not a trivial task.
Yes.
So you have to engineer the photonic material in a way that the photons effectively feel a magnetic field. And that's the so-called topological photonics, where you can also look at this review paper by Tomoki Ozawa et al. It's again a review of Modfies. This is from 2019. That's on so-called topological photonics. It's basically the field where you make photons to behave like particles which are subject to some magnetic field. It's called the synthetic magnetic field.
Yeah. Okay. No, I was confused about this Hall because I didn't connect it with Hall effect. I rather went to the electron Hall, the thing, but okay, now it's clear. Well, clear to know what is it about. Thank you very much.
Thank you.
Thank you for the question. Are there any other questions left? Feel free to ask. Professor Carusotto, maybe you have something to tell us additional.
I don't know if you have some further curiosities. No, if it's some point on which you think I can speak more, I would be happy.
Okay. I think for now we
I think like for the topological photonics, we can also have another time, another lecture, because I guess this lecture was very clear. I guess that's why there are not a lot of questions. And maybe for the next time, we can again arrange another meeting and have another full lecture about this one, as we have discussed already.
Yes, sir.
Okay.
I think, Tatev, if you are interested, I'm really looking forward to it. So
all right.
It'll be
yes,
great
I
fun
am.
to chat with you. So I'll be happy just
all right.
to think when it would be a good moment for you and the students, and just let me know. I'll be very happy.
Thank you very
thanks
much.
A lot
thanks
for
a
the
lot.
invitation. It was, as usual, great fun to chat with you.
Thank you.
Thank you very much.
So now we'll talk Professor Saharyan, who will talk about radiation of surface polaritons and cylindrical waveguides. So please, Iacopo. Yeah.
I should have stopped my sharing. Good.
Yes.
So
You
good.
Yeah. Yes.
Good. I will. I have to just stop my.
Can I start?
Yes, please.
Okay, thank you. Is it okay?
Yes, it's clear since.
Just a minute. Okay. I'm going to speak about some recent results obtained in our group, and these results are related to the radiation of surface polaritons in cylindrical waveguides. In fact, this work continues our previous work related to the influence of media on various radiation processes. And the talk will be constructed as follows. I will speak firstly about some radiation processes in media, and then some words about surface plasmon polaritons, and then I will consider two geometries. The first one is the radiation of surface polaritons in cylindrical waveguides when the charged particle rotates around the waveguide, and the second one is the radiation when a charged particle moves along the rectilinear trajectory outside of the cylindrical waveguides, and after that I make some conclusions related to the results. First of all, of course, we know that the charged particles interacting with media give rise to a number of radiation processes, and I listed here some of these ones. This first is the Cherenkov radiation, transition radiation, diffraction, and Smith parcel radiations, and also parametric X radiation. Some simple words about this. Cherenkov radiation is produced when the charged particle moves in a homogeneous medium and the velocity of the particle is larger than the velocity of the light in the medium. In this case, some front is formed. This is the result of constructive interference of elementary waves radiated by a charged particle, and we have the wave front which propagates along the direction determined by this angle theta, and this is theta is determined by the velocity of particles. And Cherenkov, this type of radiation is widely used to detect charged particles, to detect cosmic rays, and there are many types of Cherenkov detectors, and it plays an important role in particle physics. Another type of radiation is the transition radiation. This radiation arises when a charged particle or the beam of particles crosses the boundary interface between two media which differ by the electric properties. And this radiation is predicted by Tam and Frank, and this, in fact, it has the same nature as the Cherenkov radiation. In fact, the radiation is the energy is radiated by media, but media is excited by the charged particle. And again, the transition radiation now is widely used for the diagnostics of particle beams in accelerators, and also as a source of electromagnetic radiation in various ranges of the spectra. Parameters of the intensity and the distribution of the radiation can be controlled by using the periodic structures, and in this case the radiation is called the resonance transition radiation. In this case we have the constructed interference of the radiation from different interfaces, and as a periodic structure we can use, for example, stack of plates, photonic crystals, or acoustic waves. In particular, we have some investigations related to the radiation of transition radiation on acoustic waves. In this case, we can easily control the period of the periodic structure. And another example is the diffraction radiation. In this case, we have the radiation, and when the charged particle moves near the media, and again, the physical nature of the radiation is the same. The charged particle polarizes the media, and when equilibrium state is reached, in this case, during this process, the radiation is formed. If we consider the diffraction radiation on periodic structures, this is called the Smith-Parcel radiation, firstly detected experimentally by Smith and Parcel. And in this case, the spectrum, if you have periodic structure, the spectrum of the radiation along a given direction is quasi-discrete. And here it is shown that in a forward direction, the radiation frequency is higher than in the backward direction. An example, a very important example of the electromagnetic waves. In fact, this is the mixture of the electromagnetic waves with electron waves in metals. These types of electromagnetic modes are called the surface plasmon polaritons. They are an important example of the surface waves, and they are actively studied at this moment, related to wide applications in various fields. I have listed here some of them. This includes surface imaging, surface enhanced Raman spectroscopy, data storage, biosensors, and so on. These are, as I said, the important type of the electromagnetic radiation. And just some words about the surface plasmon polaritons. They are evanescent electromagnetic waves. They propagate along the interface of metal dielectric, and it is a result of collective oscillations of electrons and electromagnetic field. These are the surface waves. This means that the energy of this wave energy is exponentially decreasing on both sides of the interface. You can see here as this plus and minus this electron part, and this one is the electromagnetic part. Here just one mechanism is indicated when usual photon interacts with the interface. In this case, the energy of the photon transforms to the energy of surface plasmon polaritons. But in order to have these special types of waves, you should have this exotic situation when the dielectric permittivities of this neighboring media should have opposite sides. For example, this takes place if, for example, from one side you can take the vacuum, and from another side you should have metal, and the electric permittivity should be in the spectral range, where the permittivity of this metal, real part of permittivity, should be negative. Here I have listed remarkable properties of the surface plasmon polaritons, that we can have here the very high concentration of energy. Also, we can work beyond the diffraction limit, which is not possible by using the usual electromagnetic phase. Of course, these surface plasmon polaritons are most thoroughly investigated type surface waves, but another surface waves also can exist. And instead of metal, you can use, for example, doped semiconductors, inorganic dielectrics, ionic crystals, and so on. Related to doped semiconductors, the good thing is that here you can control the radiation frequency by using the density of the doped material. And this can control the plasma frequency of the material. And this means that also you can control the frequency of the surface plasmon polaritons. An important direction is to develop sources of the surface plasmon polaritons in the infrared and terahertz ranges of frequencies. This can be done, as I said, by using doped semiconductors or by using artificially constructed materials. It is good that by using these metamaterials, it is possible to control the properties of the electric permittivity, in particular to have the electric permittivity with a negative real part. Here I have listed some generation schemes for the surface polaritons. They include prismed grating couplings, strongly focused optical beams when the energy of photons is transformed to the energy of surface polaritons. Another example mechanism for the generation is guided photonic modes from another waveguide. You connect just two waveguides. From one waveguide with usual photons, you can generate in the second waveguide the surface plasmon polaritons. And the last example here is the radiation of surface polaritons by using the charged particles. In fact, the first experimental observation of surface plasmon polaritons was based on the measurements of the electron energy loss spectra. So just first problem, as I said, is the following. Here the geometry is presented. We have some dielectric waveguide with the electric permittivity epsilon 0, and this waveguide is immersed in a homogeneous medium with permittivity epsilon 1. In particular, you can have a vacuum as an exterior region, and our point charge Q rotates along this circular trajectory along the dielectric permittivity. Here we can have three types of radiation. The first one is the just usual synchrotron radiation in the exterior medium, and this synchrotron radiation can be essentially influenced by the presence of the electric waveguide, and we have some work related to this topic. If Cherenkov condition is obeyed in the exterior medium, you also can have Cherenkov radiation. Another type of radiation is the radiation with guided modes. These are the volume modes which propagate inside the dielectric waveguide. The corresponding wave numbers is determined by the transcendental equation for this dielectric waveguide. And another example is the radiation of surface polaritons, of course, in the spectral range, where the dielectric permittivities of the cylinder and exterior medium, they have different signs, as I said. If the Cherenkov condition is satisfied for the charge, for the image of the charge on the cylinder surface, this is here. This is the Cherenkov condition. You see, epsilon 0 is the the electric permittivity of the cylinder, and v tilde is the velocity of the particle image, particle projection on the cylinder surface. If this condition is satisfied, in the exterior region, you will have some strong peaks. And at these peaks, the radiation intensity by orders of magnitude can be stronger than the radiation, usual synchrotron radiation in homogeneous medium or in the vacuum. And in fact, we have shown that these modes, these peaks, are closely related to the equation of the eigenmodes for the electric cylinder. You just should this Hankel function replaced by the Neyman function. And this replacement is very good, is in very good agreement with the numerical investigation. In the second time, we have also the radiation which propagates inside the cylinder. Of course, our motion is periodic, and the radiation frequency just will be the multiple of this main frequency. This is the frequency of the rotation for the charge particle. And these two quantities, lambda g, defined by this relation, play very important role. If this lambda 1 is evaluated by using the electric permittivity of the exterior medium. If this lambda 1 square is smaller than 0, in the exterior medium, we will not have the volume waves. This means that in this case, only we will have the waves which propagate inside the waveguide. And this is seen from this McDonald function. This is the electromagnetic field outside the electric cylinder is determined, the radial dependence, by this McDonald function. And you know that this is exponentially decaying if this r is lambda 1 r is larger than 1. And in fact, at distances larger than the distance of the order of wavelength, you will have exponential decrease of the electromagnetic fields. For guiding modes, the interior dependence of this of the electromagnetic fields is determined by the usual Bessel function. This is the Bessel function, and lambda 0 is evaluated by using the permittivity of the electric waveguide. Here we assume that surrounding medium have positive electric permittivity. In fact, in particular, we can take vacuum. And for guiding modes, this lambda 0 square is positive. This means that guiding modes are volumic modes inside the cylinder. Surface type modes are present when this lambda 0 square is smaller than 0. In this case, the radiation field depends on the radial coordinate by this modified function, and it is known that if r increases, this exponentially increases. This means that this field is mainly located near the boundary between cylinder and between the exterior medium. And as I said, these surface type modes are present under the condition when the epsilon 0 is smaller than 1. If, in fact, in the literature, the surface polaritons are mainly investigated for planar boundaries, and from the result, or our result, by taking this limit, you can obtain the results for planar boundary. Here I present some results for the numerical investigation of the radiation for guided modes, these volumic modes. Here is the number of quanta radiated on the given harmonic n. And this for electron, for example, this is q square over 2ht. This is just 137. And here are given the parameters for which these numerical calculations are presented. This red points corresponds to the radiation when you have vacuum just. This is the synchrotron radiation usually. And these black points correspond to the case when the dielectric cylinder is present. You can see that, and this is the harmonic. On some harmonic, you can have some essential increase of the number of radiated quanta. This means that the electric, in this case, we have some modes which propagate inside the electric waveguide. These are guided modes, and you can have essential increase related to the presence of this the electric waveguide. But the main point for me here is the radiation of surface type waves. As I said, for surface type waves, we should work in the spectral range where the electric permittivity is smaller than is negative. And in this case, you can see that the z component of the wave vector, this z component is the wave vector along the axis of the cylinder. This is larger than, this means that the corresponding radiation wavelength can be essentially smaller than for the guided modes. Here I show that on which values of this, in fact, this wave vector takes discrete values. It is determined by the eigenvalue equation for the dielectric cylinder, and this is given by this equation. Here I and k are the most modified Bessel functions, and you should solve this equation with respect to kz. For a given n, you will obtain some number of roots, and these roots are numbered by this s, index s. And having this, you can find this lambda 0 and lambda 1, and these functions are evaluated with these arguments. Of course, this is a complex transcendental equation, and you should use some numerical methods. We first find these roots, and after that we evaluate the radiation intensity, and here this radiation intensity is presented. This is the formula for the genesis, exact formula. In fact, this exact formula, of course, we work in classical electrodynamics, but in all other cases, this is exact. This also works in the case when, for example, you have the complex dielectric permittivity, when the permittivity has imaginary part. And I present here some numerical results. Here I have taken as an exterior medium vacuum, epsilon 1 is 1. This RC is the radius of cylinder, and RQ is the radius of the charge orbit. And this is this, and this we have evaluated this number of radiated surface polaritons for two cases of velocity. The first one is V over C is 0.5, and the second one is 0.95. And here the full curves correspond to the radiation on the harmonic n equal to 1. This is the main harmonic, and the dashed curves correspond to the second harmonic. And you can see that here we have, you see the number of these radiated plasmons, you can see can be essentially large. You can remember what was the situation for the guiding modes. You see here you have just the order of 10, but in the case of plasmonic waves, it can be essentially large. Then just a few words about the second. Here, again, yeah, I have presented the results for the guiding modes. And for the guiding modes, you see, again, I have presented the numerical data for this velocity, 0.95, and again, for this ratio of the orbits. Here is the radiation intensity depending on epsilon 0. Of course, for guided modes, epsilon 0 is positive, and here is n equal to 2. You see, here we have just order of 1 for this number. And for the plasmonic case, we have essentially large number compared to the guided modes. And the second problem is the case when a charged particle moves along this rectilinear trajectory outside of the dielectric waveguide. In this case, if the Cherenkov condition in the exterior medium is satisfied, that means that we have this condition. In this case, we have Cherenkov radiation in the exterior medium. And this Cherenkov radiation is propagating along the direction that is determined by this angle, This is the standard Cherenkov angle. And we evaluate, of course, here, in contrast to the previous case, here the spectrum is continuous. This omega frequency takes continuous values, and for that reason, here I consider the spectral density of the radiation intensity, and this is the spectral density for the radiation quanta radiated per unit length of this trajectory. And in order to compare with the radiation in a homogeneous medium, when this dielectric cylinder is absent, you just have usual Cherenkov radiation, and from the well-known formula for the Cherenkov radiation, the result is this. You see, if you don't take into account the dispersion, this is just the constant quantity. This is dependent completely by the velocity of the particle. Now let us compare this in order to see how this dielectric waveguide acts on the Cherenkov radiation in the exterior medium. Here I consider two cases. The first one, for example, I have taken epsilon 0 is 1. This means that you have some cylindrical hole inside the homogeneous medium with the electric permittivity epsilon 1 equal to 3.8. And the calculations were done for the electron energy to MeV. This is the ratio. This is the ratio of the radiation in the presence of cylinder and to the radiation when the cylinder is absent. This is the standard Cherenkov radiation. And this is the result for this case. Here, the calculations were done for different values of this ratio. R0 is the distance of the trajectory from the axis of cylinder. For different cases, you see this is the case. This is the one, this corresponds to the radiation in a homogeneous medium, and you will have this some oscillations as a action of waveguide. But now you can see that the situation is drastically changed if we consider the dielectric permittivity of the cylinder is larger than the dielectric permittivity of the surrounding medium. Of course, in this surrounding medium, I cannot take here the vacuum just for that Cherenkov radiation is absent in the vacuum. And in this case, you can see that from this graph, we can have some interesting thing. In fact, Cherenkov radiation spectrum becomes some quasi-discrete. And at these peaks, the radiation intensity can essentially, for example, here, about 5 times be larger than the radiation intensity in the homogeneous medium. This is some characteristic feature which is obtained only in the case when the permittivity of the cylinder is larger than the permittivity of the surrounding medium. And here I present some results for the radiation of course, here you will have 2 cases. If epsilon 0 is larger than positive, you will have guiding modes, and we have evaluated the number of these modes radiated by discharge, and also you will have surface polaritons again. If you work in the spectral range where epsilon 0 is negative. And here I present the results for the radiation of surface polaritons on a given given frequency. It is here the frequency and the wave number are related by this simple relation. Just for that, you have this simple rectilinear motion. This is the case also for the Cherenkov radiation. Again, we determine this K and S from the eigenvalue equation for the waveguide, and by using this, we evaluate this radiation intensity by using this formula. Again, this is exact formula. And here I have presented the number of radiated surface polaritons as a function of the frequency. Again, you can see this, we can have a sufficiently large number of radiated surface polaritons. These are given for various values of the particle motion. So I have finished my talk, and as I have shown that the presence of cylindrical waveguide may essentially influence the characteristics of various types of radiation. It includes the synchrotron radiation outside the medium, Cherenkov radiation in the exterior medium, and also we can have the radiation of guiding modes if the electric permittivity of the cylinder is positive, and also we can have the radiation of surface polaritons, and in some cases the number of quanta for radiated surface polaritons can be essentially larger than the number of guiding modes. And this is the one. Thank you for attention.
Thank you for your talk, Professor Saharyan. I have a question.
Okay.
Can you go back to the slide of radiated quantas?
This one?
The previous.
Or guiding modes?
Yep, this one.
These are for guiding modes.
Mm-hmm. So is there any way, or can we somehow calculate the effective radius of cylinder so that the number of radiated quantas is the maximum?
In fact, here you can note that I have not fixed the radius of the cylinder and also the radius of the charge rotation. In fact, this all result depends just on the ratio, but the absolute value of the radiated frequency, it depends on the radius of the cylinder. In fact, it is of the order of radius of cylinder. In the second problem, when charge moves, it can be essentially larger, but in this case, it has the same order. For example, you can take the cylinder with a radius of 1 millimeter, order of 5 millimeter. In this case, you can have radiation in the terahertz range or slightly smaller. Mm-hmm. But in the second cases, by using relativistic effects, you can have frequencies which are gamma factor types larger than the frequency of this case. And just for that here, just a comment, why this you have this such drastic increase? This is related to that for this value, some new mode of the electric waveguide appears. If you change the parameters, some new modes appear. And when these modes appear, you will have some increase of this radiation. You can see some smaller increase in this case also. This means that by choosing the radius of waveguide, you can have radiations in various ranges of the spectra.
Okay, and for the negative epsilon values,
yeah,
when we had that, can we say that the space not included the cylinder part is the dielectric, and the particle is rotating there in the dielectric part?
In fact, usually plasmonic surface waves, they are considered for metals. But the main problem is that in the spectral range where this permittivity is negative, the absorption is high. The imaginary part also is relatively large. And the main problem in plasmonics is just to have some materials which have the small negative part. This can be reached, for example, in the terahertz range or slightly slower by using metamaterials. This is very important direction in this investigation. As I said, the main problem is to have negative real part, but small imaginary part of the electric permittivity, and this is the main problem.
Okay, and for the absorption part included, do we have again the effective this value of radius or not?
In fact, here, for example, now there are waveguides having the radius having this nanometer.
Okay.
And in this case, it can be very small. For example, but also you can have effective waveguides in crystals. For example, if you have some channeling radiation In fact, crystal works like some channel, which just the channel in radiation is similar this type of radiation. In some cases, we have also considered the helical motion of the particle. This helical motion is the mix of these two problems. You have some rectilinear motion alone and also some rotation.
Oh, okay. Thank you.
Thank you.
Datev, go ahead.
Yes, thanks a lot for this nice presentation. I have a question exactly to continue what you have just mentioned about the nano size, nano radiuses. So what are the smallest sizes of the cylindrical waveguides that can still work with the same considered conditions? Because in the end of the day, these kind of cylinders can be used as nanoparticles for surface enhanced Raman spectroscopy measurements, right?
Yeah, of
so
course.
What are the dimensional limitations to still be able to use the same conditions as you mentioned here?
Yes, but here, for example, in the first problem, the main problem is that it is difficult to have a particle rotating with this small radius. If you use magnetic fields, this magnetic field should be very strong. But if you use some magnetic fields which are acceptable, not acceptable, but which we can reach in laboratories now, you can have one of the order of 1 millimeter. But for example, in crystalline ondulators, in this case, crystal field creates this. And it is not the magnetic field as a source of this trajectory. In that case, you can have, for example, in crystals, in spiral ondulators, you have this type of motion.
Okay.
But of course, you should be careful in this to have. You should have some small imaginary part of the electric transmittivity, and the most difficult part is that.
Okay, and as you mentioned, metamaterials are kind of solution for this case, right? Yes.
If you, for example, create some metamaterial with some elementary elements smaller than the wave length, and it is very promising direction of this field.
Okay, thank you very much.
Thank you.
Okay, thanks for the question. Oleg has a question, so please go ahead, Oleg.
Thank you. Would you say how did you get the radiation intensity equation? I think it was the next equation, next slide.
Okay, I will just show. We have,
yes.
In fact, you see, we have evaluated in two ways. For example, if we consider the radiation in the exterior medium, we evaluate the radiation intensity by using the Poynting vector, just the flow of the energy. But for example, we can also evaluate the total energy. Total energy is evaluated just the work done by the radiation field on the source. And this is given by this formula. But this includes all the types of radiation. And it is interesting that we have checked that if you evaluate these, all the contributions, and also you evaluate separate parts by using the Poynting vector, we have checked that the sum of this will give this one. This is just an additional check for our calculations.
Thank you. And the slide before, could you go one before?
Before?
Slide before. Yes. Yes, this one. So this equation determining the aging values of the projection. What is this equation?
This equation, this UN equal to 0. This is the equation.
What is UN?
UN, you see, this is the left side, you see, UN. This is just after the equation determining this equation. This is the transcendental equation.
But how did you get this equation?
This equation is obtained we evaluate the electromagnetic field. We evaluate the Fourier image of the field. Fourier image has poles as a function of complex variable kz. And these poles are zeros. These poles are the solutions of the eigenvalues of the electric cylinder. This means that this equation, in fact, determines the poles of the Fourier image of the electromagnetic field. These are the eigenmodes of it. For example, for general, you can find this general case in a Jackson book of classical electrodynamics.
Thank you.
It is interesting that if you take the limit epsilon 1 goes to infinity, you will obtain the radiation in metallic waveguides. Just in that case, of course, you will have just the radiation inside the waveguide.
Okay, thank you.
Thank you.
Okay, thanks for the question and for the answer. Are there any other questions left? No one got a question? Okay. Professor Saharyan, if I ask you, can you turn off your sharing? Okay. Please, everyone, turn on your cameras so that I can have a screenshot from our webinar.
Yes, and again, thanks a lot, Professor Saharyan, for this very nice presentation, because I indeed work with surface plasma resonance and surface enhanced Raman spectroscopy. So it's very close to my topic. It was very interesting to see the things from the theoretical point of view, because I do all the experimental work and barely go into the very deep depth to the theory. It was very nice.
Okay, thank you. And for us also, it is very important just to see what can we do in order to be closer to the real situation. Of course, we have some idealized problem, which is exactly solved. But in nature, of course, problems are not exactly solved.
Yeah, so we can definitely discuss later, later theory and experiment, yeah?
Sure.
Okay.
Please smile.
Okay, thank you.
Please smile.
No one else is turning on the camera. Okay.
I guess no. Okay. Thank you very much. I guess.
Thank you.
Yep, that's it.
Okay, thanks a lot. So again, thanks, Gor, for moderating the session. To our speakers, it was very, very interesting day of 2 theoretical lectures. For me, especially as an experimentator, to hear from the other side of the story. And the series of these webinars will definitely continue. And hopefully next time we'll have more attendees. And thanks again. Have a nice day.
Thank you.
See you soon.
Bye. Goodbye.
Thank you very much.